really be too tough to do. It's really just only ever going to be a matter of why you're doing what you're doing and what the results mean. Okay? But when you're looking at A dot B times C, where C is another vector, A dot B, even though it's a product of two vectors, the result is going to be a scalar. All right, so if we dot A against B, we're taking the 1, multiplying it by 0, adding to that the 2 multiplied by the 2, and adding to that the -3 multiplied by the 4. All right, so 0 plus 4 minus 12 looks like a -8 for at least that part of it. And then that -8 gets multiplied as a scalar against the 5, -1, 3. And there are functions in GeoGebra that'll do dot products for you, but it's kind of like, you know, it's just simple arithmetic, so it's not really a necessary thing to worry about, right? So yeah, you get -40, 8, and -24. Oh, yeah. No, I confused myself there for a second. I was like, wait a minute, it should be a scalar, but it's not. It's not a dot product anymore. Now it's a scalar multiplication, right? So that's what I was talking about last class when I said just be careful when a question asks you to find a scalar product. Here we found a scalar product. You know, in the second step, it's just it wasn't the dot product anymore because it's a scalar multiplier against a vector. Right? So it's just a little quirkiness in the verbiage. Oh, okay. Let me just double check for attendance. All right, Michael, I got you now. All right, you're all set. All right, so A dot 2 multiplied by C. So we're dotting A against 2 multiplied against C. So we'll take care of the 2 times C first. So we're really looking for the dot product of 1, 2, -3. And this one we could kind of do on the fly because we're just doubling the entries in C. So 10, -2, 6. All right, so that takes care of this piece. So then it's just a matter of carrying out the dotting action here. So we're looking at 10 plus -4 plus -18. So is that -24? No. 6 minus 18, -12. I think I might have. I don't even know what I was thinking. Yeah, I sometimes try to figure out why I say stupid things, and sometimes there just isn't an answer. There isn't an answer for me. You know, so it's just the wrong thing comes out of my mouth sometimes, and that's an ongoing, lifelong issue. Most of the time, it's just incorrect. As I've gotten older, I've gotten away from incorrect and embarrassing things coming out of my mouth. Now it's just incorrect things coming out of my mouth. It's improvement. Yeah, so I don't say too many dumb things anymore. That's the growing up process. Anyway, so those are the skills that we were talking about. You know, there's kind of a little twist along the way where you kind of look at it and say, okay, well, this is all stuff that we know, and twist isn't really the right word, but it's like what's the point? Like, why are we talking about this? And it's like, well, let's just take a look at that example 4 again, and let's say we had A dot 2C, but I thought of this as 2 multiplied by A dot C. All right, so I'm actually going to figure out this one here because then the A dot C I could just kind of figure out on the fly here. So this piece, I'd be looking at, we got a 5 plus a -2 plus a -9, which gives you a -6, and then you bring down the 2 after the fact, and you get a result of -12. All right, so the rationale behind this, you know, selecting this problem in particular, is to really enforce this idea or reinforce this idea of scalar multiples, but it really kind of gets at the associative property. All right, so looking at this rule here, right, I'm kind of off of my highlighting. I'll go purple on that one. So that one's really kind of justifying this relationship. Let me get a pencil, a purple pencil here. All right, they go hand in hand. All right, so that's really what these examples are all about. They're really trying to get at, you know, the operations that wouldn't necessarily be obvious, right? So, you know, depending on what it is you're working on, you may look at it and say, well, I wouldn't care about those properties. And then in other cases, you say, well, oh, that was a good one. That was an important one. I'm glad I made use of that. You know, it all varies from problem to problem. All right. So let's kick on over to page 15 and talk about how we evaluate a dot product using trigonometric functions. So we have a rule here. Another way of representing the dot product is u dot v is equal to the magnitudes of u and v multiplied by the cosine of the angle separating u and v. All right. So we're just going to prove this real quick, but yeah, there's a thing staring at you right there, that v minus u. Like when I first saw this proof, I was like, all right, well, someone's going to have to explain to me where the hell that v minus u came from. All right. So of course nobody did. And so I explained it to myself eventually. And it has to do with vector addition, right? So if I can think of, let me just get a blue here, v minus u as the same as saying v plus negative u, then what I can do is I can create a vector negative u, but then just shoot that off in the negative direction, all right, and call that negative u. All right. Now, I like using the parallelogram approach when it comes to finding vector sums, which is to say the two relevant vectors, the two that we care about. So I got vectors u and v, but in this case, I'm using negative u and negative v. What I do is I create negative u and positive v. Crash. Oh, wrong app. Ooh, batting 1,000. Gets there eventually. I learned that this only happens when I have too many files open and my GoodNotes app is trying to update them all and back them all up at the same time, and it just says, I give up, fresh start. So I'll just kind of have to deal with that for now, fix it later. All right, but I'm going to create a parallelogram here. And you know what? Let me just leave the purple one there. Add v so we know what it is that we're adding. All right, I'm going to pop the negative u here. Now, if I want to find the sum of negative u and v, or v plus negative u, one way of handling that would be to find the diagonal of this parallelogram, the relevant diagonal, of course, which would be this one right here. So that's v plus negative u, or negative u plus v, either way. Now, as it turns out, when I create this parallelogram, so let me just accentuate it a little bit here, see if I can actually make it look halfway decent. Is it going to know that I'm trying to create? Yeah, I kind of do. All right, I'll take it. So in trying to figure out the diagonal for this parallelogram, I inadvertently, although it worked out in a really nice way, I inadvertently created another parallelogram for which V is the diagonal. That would have been nice, but it didn't play out the way I would have. But you know what I think I can do? I think you can resize and try to get. All right, we're just going to pretend that that looks beautiful. All right, so we inadvertently created another parallelogram, and since opposite sides in a parallelogram are congruent, let me go back to like 1.0 on this. That makes this side congruent to this side. So whatever the vector is for one would necessarily have to be the vector for the other, and also their magnitudes. Right? So it's just they're pinned at different locations, but that's okay. Right? So that's all of that is to justify why we say that the third side between two vectors, if we just connect them directly, is the difference between the two vectors. All right. So it's like, okay, that's a lot for something that we could just memorize. But you've kind of gotten a sense where possible, where I don't have to teach an entire course to explain a concept to you. I prefer to give you the origin story behind this stuff, because it's like, if you get it, then you don't have to memorize something, and that's always a good thing, right? So all that being said, I can kind of, I'll bring all this back in a second, but we do have just this piece of information that we're really interested in, right? So let me just that piece of information is the one that we're I brought up theta along for the ride. Hold on. Nah, I'll just live with it. White it out. All right. So we're still working off of that triangle, but now we know why that triangle exists in the form that it does. All right. So what we can say is that, yeah, well, it's not necessarily a right triangle. So we can go using our rules of trigonometry. We can say, based on the fact that we're given three sides and an included angle, that the law of cosines would apply. All right. So I'll just jot it down over here. Law of cosines. One variation of it, c squared is equal to a squared plus b squared minus 2ab cosine c, at the corresponding angle applying to the given side, or the side that's isolated. So we have a theta here that's opposite of v minus u. Right? Now these are vectors. You can't just say that a vector is the length of a side. A vector it has magnitude and direction. I mean, there's a lot going on there. But what we can do is slap some magnitudes on there and just go with the lengths of each side, because the length of each side would be the magnitude of each vector. So regardless of where the vector is pinned, whether it's at the origin or some other location, we could then say that these are now measures of the sides of the triangle, all right, which is all good. So now I can say that the magnitude of v minus u squared is equal to the magnitude of u squared plus the magnitude of v squared. Of course, I boxed myself into a corner here. I painted myself into a corner. I don't even know what boxing myself into a corner means. V squared minus 2 u v cosine of theta. All right, we don't know what theta is, but we do have at least measures for the lengths of the sides. Now, we're not going to be able to simplify anything until we do something about the left-hand side. Now, that left-hand side, yeah, it's made up of vector quantities, but it's also a binomial. So we can go through the process of distributing it out. However, we do have that little recall statement that's thrown right in front of us, and that has to do with the fact that a magnitude squared is equal to the dot product between two vectors, right? So we could actually make use of that fact, right? So I can say that the left-hand side is v minus u dotted against v minus u. And just kind of work the left-hand side. Now, if things don't start canceling out here, then we're in trouble, because then this is all for nothing. But we do know that we're supposed to get this rule here, so things better cancel out, and they're gonna cancel out. So what we're gonna do is look at this as the product of vectors. Now we're dotting them against one another. So I'm going to say v dot v FOIL method, right? So outers negative u dot v, another negative u dot v, plus u dot u. Yeah. Now, v, u, they're not magnitudes in this context. We converted it over using one of the properties on the previous page. So I can't write v squared. That doesn't have any meaning. That's like taking a coordinate and squaring it. You know, if I were to tell you the coordinate 1, 2, 3, you would say, okay, well, what do you want me to do with it? Square it. Say, what the hell does that mean? Square each part? Square one of them? Square what? What are we talking about? Okay. So that's the same idea here, but we can square their corresponding magnitudes. And that's important because if we go back to that rule, we can say, wait a minute, v dot v is the same as magnitude of v squared. U dot u is the same as magnitude of u squared. So magnitude of v squared minus, we can combine like terms, fortunately, 2u dot v plus magnitude of u squared. And we can combine the like terms because of the scalar multiple rules that we were talking about on the previous page. They allow for that. All right. So I think I'm taking along the picture for the ride here. So let me turn that feature off. Releasing. Don't want that. They're still on the screen. All right. So then once we get to this step, we're in a pretty good shape because we have a common magnitude of v squared on both sides, common magnitude of u squared on both sides. Those will cancel away. The remaining expression has a common -2 that can cancel away. And so I get u dot v is equal to the magnitude of u multiplied by the magnitude of v multiplied by the cosine of theta. Which is what the rule is. That's pretty cool, right? An extension of that, pretty cooler, I guess. I want to take liberties with wording. if I take, I'm just going to go like this and make a fraction bar. If I take the UV magnitudes and divide them from both sides, I get a new relationship here that tells me that the cosine of theta is equal to the dot product of u and v divided by the magnitudes multiplied. I can go a further step and find the inverse cosine of both sides. And now have a means for figuring out the value of theta. Right, that would be the angle separating two vectors within a system. Could be a two-dimensional system, three-dimensional system, could be anything. And a lot of possibilities here. So a lot of good stuff here. Kind of clean that up a little bit. So in the question here says, find the measure of the angle between the pair of vectors. I would just need, first off, to find the dot product between them, then find the magnitudes multiplied, and then inverse cosine of that result. All right. So I could look at this and say, all right, well, I got, well, you could put it in component form if you want, but it's easy to pull out the coefficients. All right. So one of them I'd call u, the other I'd call v. This is 1, 1, 1. 2, -1, -3, u dot v would be equal to 2 plus -1 plus -3. So 2 minus 1 is 1. So -2 would be the dot product, unless I screwed that up, entirely possible, of course. Then I need the dot of u. I'm sorry, the magnitude of u. Square each component, add them together, then take the root. If you want, dot it against itself and take the square root, but that's the same thing. All right, so this is the square root of 3. I got to imagine I'm not the only one in the world where it's like, if the landline rings, you're like, well, clearly it's a telemarketer because I don't give out that number to anyone. So why would anybody be calling me there? So 2 squared plus 1 squared plus 3 squared, we can ditch the negatives because they're going to square away anyway. So 4, 5, 9, so rad 14. All right, so we're looking at cosine of theta is equal to -2 over rad 42 if you multiply them together. Theta would be equal to the inverse. Why am I putting a radical then? Jeez. Long week. So function, trig, inverse cosine, -2 divided by root 42. So we get 1.88 radians-ish. Or if you want to go over to degrees, you can. Just hit that little wrench, tap on degrees. It'll convert it over for you, approximately 108 degrees. All right, so that one's, you know, it's got a little, I don't want to say it's got teeth to it, but it's got some work. You know, you got to do some stuff. The next one, same idea. You know, it helps if you want to have an organized approach to denote the two given vectors as something, typically u and v. So we call the first one u and the second one v. So the first step in the process would be dotting the u and v. So -2 plus -20 plus 24. All right, and that gives you, oh, sorry, -4. that gives you a result of 0. Now on the bottom, we need to get, when we figure out our cosine of theta, we need to get the product of magnitude of u and v. Now, because the top is equal to 0, I honestly do not care one bit what that denominator is, as long as it's not 0. Right? And just by looking at the vectors, I know that's not going to be the case. U times v, the magnitudes, are not going to be equal to 0, because neither of them are the 0 vector. Right? The only way it would play out is if one of them, and actually, I guess there's other ways that it could work, but that it could play out, but I'm just not thinking of any. It would have to, I would imagine, involve some imaginary numbers or something like that. It's just something not occurring to me. But so I don't want to dismiss any other possibility because I'm just not thinking of it. But you'd have to have one or both of the magnitudes themselves be equal to 0. In order for that to happen, the length of the vector would have to be 0, right? And the only way I can think of for that to happen would be is that if it was the 0 vector, right? 0, 0, 0. And that didn't happen, right? So theta is going to be equal to the inverse cosine of 0 over something that's not 0, but like, do you want to write non-zero? I don't know. I'm going to write u dot v. And in this case, we're talking pi over 2 radians, or 90 degrees, just by knowing your unit circle. But maybe you don't. So you just put it in 0 over whatever. All right, go back into radian form. Pi over 2. All right, pi is 3.14. This is half of that. So there you go. All right. So that means that these two vectors are going to be perpendicular to one another. But the thing is, it's perpendicular in three-dimensional space. So perpendicular could be really in a variety of different orientations. When we think of perpendicular in two-dimensional space, we think of it on a flat piece of paper where perpendicular represents usually one is going vertically and the other is going horizontally. So there's your perpendicular, right? It could also be maybe one's going at a 45-degree angle and the other's going at a 135-degree angle. If I can get my orientation in my hand to look reasonably decent in the camera. X-Men. But in three-dimensional space, you also have the skew aspect of it, right? So I'll show you really quickly. I never have my, if I were more organized, I would be able to illustrate this stuff because I'd have all my manipulatives with me. But here's some things that are orthogonal. All right. So I'm showing you right now an Apple Pencil and an Apple TV remote that are orthogonal. All right. Now, you don't necessarily know that based off of the perspective because it's pointing straight at you. But if I turn it, you can see that it appears to be orthogonal anyway. All right, roughly anyway. But if I go like this, all right, if I go like this and I show you, okay, these two vectors are orthogonal, or if I were to even say, tell me whether these two vectors are orthogonal, you might say, which two vectors are you talking about? And I'd say, these two. Aha, it's hiding one behind the other, all right? They're orthogonal, as in perpendicular in three-dimensional space, but you would never know just by looking at it because of the perspective. But if I change the perspective, the orientation, it's easy to see, all right? So that's why we need an approach, an analytic approach, to be able to come up with this stuff, because sometimes you could have lines that intersect with one another in three-dimensional space, but don't look like it. You could have lines that don't intersect with one another that do look like it. So if I show you, okay, these two lines are intersecting, right? Absolutely, there's no doubt in your mind. And then I change the orientation and you say, oh, wait a minute, look at that. No, they're not. They look like from this perspective that they were, but from this perspective, they're not, all right? So we need a method that's going to allow us to come up with that information that doesn't rely on just eyeballing it. In 2 dimensions, you just eyeball it. If they look like they cross, they cross. In 3 dimensions, not the same deal. Now, it turns out if neither of the vectors are the 0 vectors, so the non-zero vectors u and v are orthogonal, if and only if their dot product is equal to 0, that's a pretty quick and easy way to determine if 2 vectors are orthogonal. All right, so they're going to form a right angle with one another. Still not going to tell us if they intersect with one another, but and the vectors themselves wouldn't, but whether or not they're part of lines that would intersect. All right, so what I can do is I can dot P and Q, 10 plus 0 plus -10, result of 0, or quality 0, let's clean that up. Therefore, P and Q are orthogonal. So sometimes it's just as simple as that. Right. Let's hop on over to page 16 and talk about projections. All right. So I'm going to leave 8, 9, and 10 for you to tackle on your own. I might just go the video route for these these 3 problems. They're not difficult. They're a little on the kooky side, but they're not difficult. All right. The vector projection, though, it's another one of those things where carrying out the process is not difficult, but I absolutely want you to be able to understand what the true meaning is. All right, and you can read, I'll read the blurb to you. Definition. The vector projection of V onto U is the vector labeled proj, okay, projection of V onto U. You know, the little subscript of U is the thing that it's onto. Okay, cool. It has the same initial point as U and V, and the same direction as U, and represents the component of V that acts in the direction of U. If theta represents the angle between U and V, then by properties of magic of triangles, we know the length of the projection of V upon U or onto U is equal, or is the magnitude given as the magnitude of V times cosine of theta. When expressing cosine of theta in terms of the dot product, this becomes blah, 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 all that stuff. And you're like, okay, it was going so well until that last sentence where it was like, oh, of course, by properties of triangles. That's all textbook jargon. In fact, I believe, if I'm not too much mistaken, that's where I got this, because my kind of rule of thumb when it comes to notes is to take the stuff that doesn't make too much sense anyway, in a textbook, put it into the notes, put a spotlight on it, say, yeah, this is what they expect you to know just by looking at it. And okay, so let's talk about what the true meaning is. All right, and so in this case, what we're talking about is the interaction between 2 vectors. So if you work through the Unit P packet, you probably got through those word problems at the end that talked about, you know, the wind blowing, you know, a blimp is flying one way, a plane's going that way, the boat's going that way, the current's going that way. There's an interaction. The current has a vector that's associated with it, and the boat has a vector associated with it. The current is impacting the direction, the magnitude, and the direction of the boat. All right. So what a projection or a component is doing is just giving us the measure of the contribution of one vector towards or against another vector. Okay. So I kind of look at it like, and this is my usual analogy. So you and a buddy are carrying a couch up a flight of stairs, and you're both working together to bring that load up the flight of stairs. But at some point in the process, you're concerned that your friend is not pulling their weight. They're not doing their job, because you're feeling like it went from like it's kind of heavy to it got really heavy. And the weight of the object didn't change, It's just your friend's contribution to carrying the object. And maybe it's not even up a flight of stairs, just carrying something. You're sharing the load with somebody else. They just stopped contributing as much. All right. You are both contributing to the movement of the object, but one of you is contributing more. What we want to do is determine how much the other person is contributing towards your efforts. All right. Or you're contributing less, and we want to know, you know, like, okay, so maybe you're not contributing a whole heck of a lot, but you got to be helping at least a little bit. How much are you helping? All right. That's what a projection is doing. A good visual example is that scene in Age of Ultron, Avengers 2, where Iron Man and War Machine, or so Tony and Rhodey, because they weren't in their full armor, they were both trying to lift Thor's hammer, and they both had their just the wrist part of their suits on, and they're just trying to lift the Mjolnir. They're trying to lift the hammer. And Rhodey says, "Are you even trying? Like, are you even trying to help?" You know, like that's it. They're both like working towards a goal, and you know, they're both concerned that the other isn't doing their part. Right. So that's all this is doing. It's measuring the contribution of one or both vectors towards the other. All right. So all that's great, but what do we do? You know, how do we do it? Well, if we look at this triangle and we assume we got this whole vector u, that entire length, including that little orange arrow there, that orange vector, which we're calling the projection of u upon v upon u. That whole thing is u. What this is, this guy here represents the amount of v that's acting in the direction of u. What we want to do is come up with a way of making that a tangible value, something measurable. All right. So we know that there's going to be a theta, an angle separating those two values. And we also discovered that theta, I mean, there's a couple of different ways we can handle this, but we do know that cosine of theta is equal to u dot v over the magnitudes multiplied. That's all wonderful. We can work off of that if we want to, but we also have a more basic relationship, and it's SOHCAHTOA. Cosine of theta is equal to adjacent over hypotenuse. So I could say cosine of theta is equal to the adjacent side, which we're calling the projection of v upon u, but it's really the magnitude of that. Because again, just like before, we can't just call a vector the length of a side. It's the magnitude of that vector that's the length of a side, divided by the magnitude of v. And if we simplify, we get the relationship that we have highlighted or indicated here, and that is that the projection of v upon u is equal to the magnitude of v times the cosine of theta. Right? All useful stuff and all true. But we also learned previously that the cosine of theta, so this is where that other rule comes into play, the cosine of theta, I'll just do it over here instead of referring to it, is equal to the magnitude, the dot product of u and v multiplied or divided by the magnitudes multiplied. All right, so you would be saying projection of v upon u is equal to v, magnitude of v, multiplied by u dot v over u magnitudes, u times v. Now, magnitude of v is the same top and bottom, so we get a nice little cancellation here. And so we get the magnitude of the projection is the dot product of u and v divided by the magnitude of u. All right. So what that does is it gives us the measure of the contribution that V is offering in the direction of U. That's pretty useful information. So you even helping here? Yes, I am. And here's the value of the amount of help I'm providing. All right. Now, if we wanted to actually find the vector itself, we'd have to multiply this by a unit vector in the direction of U. All right. So that's something we talk about in the next page. But this is, we call this the component of vector V in the direction of U. All right. So just it's another term, and it's kind of annoying that we can't just live with, simple terms for simple concepts. But this guy over here is known as comp of V upon U. All right. So just another thing to add to the list of things to know, all right, and become comfortable with. All right. So the next page, I get into the derivation of that, the part where we talk about coming up with the projection of V upon U. And so what that is, so if you multiply your component, this is comp V upon U, multiplied by the unit vector in the direction of V, direction of U, what you get as a result is the projection of V upon U. All right, so all of that is for the purpose of coming up with this rule. All right, so now we just carry out the operations. So we have V and U. We're looking for the projection of V upon U, or V onto U. So if you just look at, I mean, it's a formula. The formula part is nothing. You look at that, and it's like, okay, I can follow steps. And yeah, I gotta say, when I was a student, that's what I did. Like, I didn't know what the hell this was at all. Right? In fact, I honestly don't even remember being taught this when I was a student. So I've gotten past the point where I would say, well, my teacher didn't teach this to me. Now I'm looking back at it and be like, yeah, I know myself personally well enough to know that I zoned out a whole lot more than I thought I did. That I guarantee it happened. I just wasn't listening when it did. Because if my conversations with other people at this point are any indication, I'm not even listening like 30% of the time. So I'm missing a lot of stuff. But it's great because my stress level is like way low. It's perfect. Like, you can't upset me if I don't hear what you're saying. So U dot V, great way to live. Ignorance is bliss. I'm pretty sure that's where that concept came from. So -1 times 3, -3, plus 4 times 5, 20, plus 3 times 1 is 3. So we got a 20. Magnitude of U. So the root of 1 plus 16 plus 9, get the root in there. Poor quality root. Better quality root. It would be nice if that was just one less, but it's not. So root 26. And then we have U, which we need. So that's, oh, it's U squared. Putting all this effort in to come up with a root. I don't even read my own dang formula. All right, so it's U squared, magnitude of U squared. I could have just dotted U against itself based off of that property we talked about 3 pages ago. You live, you learn. Slash, I've done this problem for 10 years, I should know. Anyway, the projection. Is going to be 20 over 26. So we're finding the quotient of these, which is really 10/13. So 10 over 13 multiplied by -143. So -10/13, 40/13, 30/13. All right. So the next one's a similar problem. So I don't want to bore you too much. I'll just bore you with number 13. I'll bore you with something. I don't want to bore you with the wrong thing. I'm leaning closer and closer to making just a solution video for the problems that I star. I haven't decided yet. We'll see how the weekend goes. But we'll take a look at number 13 because that's kind of why we're here, at least for this concept, to be able to tackle this sort of question without having to do all that stuff that we did back in Unit P, which is all those, vector additions and all that stuff. So a container ship leaves port traveling 15 degrees north of east. Its engine generates a speed of 20 knots along that path. In addition, the ocean current moves the ship northeast at a speed of 2 knots. Considering both the engine and the current, how fast is the ship moving in the direction of 15 degrees north of east? Round the answer to the nearest 2 decimal places. All right. So basically what we want to know is what contribution is the ocean making towards the movement of the boat. All right. So we know the current moves at 2 knots, but is the boat getting that full 2 knots of support? Is the wind at its back, as they say? Or is it something more like, all right, well, it's kind of going, at a skew angle, in which case maybe it's only getting like 0.9 knots out of the two available knots. All right. So we have, again, the ship container. That's going to be vector. I want to hit that. This is the ship container. Or container ship, sorry. And that's happening at 20 knots. So magnitude of V would be 20 knots. All right. In addition, the ocean current moved the ship northeast at a speed of 2 knots, considering blah, 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 blah. Okay, so we have that other angle there that's going to contribute towards this movement. Right? We just don't know, in what capacity. Right? So what we want to do, it appears anyway, is figure out the projection of W upon V. All right. And then find that magnitude. All right, because we need those numbers. All right. So we know, and we can steal the angle from this. That 45-degree angle is all wonderful, but if I drop an altitude here, we create the vector that represents the contribution. I can't even say the word. I'm like putting the emphasis on the wrong syllables. That blue arrow there is going to represent the projection of W upon V. That's the magnitude that we're looking for. Now the angle separating the two is going to be 30 degrees because the whole angle going from the easterly direction to W is equal to 45, and we already got 15 degrees going for the boat. So the rest has to be the direction that the boat and the current are separated from one another. All right. So this is, I guess, W for water. Let me go here. That's the magnitude of the, so we'll say the water current. I'll say current, because water doesn't really cost too much. The magnitude of W, they said that was equal to 2. We'll leave the units off. We'll worry about the units later. All right. So we can handle this a couple of ways. One way would be actually to use SOHCAHTOA and save ourselves some work. But the other way would be to use our rules. All right. So our rules just boil down to, what we talked about on the previous page, all this stuff. It's just the magnitude of U, I'm sorry, the dot product of U and V divided by the magnitude of U. All right. So we just have to convert that over into V's and W's. All right. So you're going to find the dot product between the two vectors. It's just you're finding the magnitude of the one that you're mapping onto. Right? So, and then you would also have to multiply by the unit vector in the direction of whatever if you wanted to find the projection. But we're not interested in that. We're just interested in the magnitude in this case. All right. So here would be V dotted with W divided by the magnitude of V. All right. Now, they didn't give us any actual vectors, but they gave us enough to make a determination of what those vector values would be. All right. So for this, we got to kind of go back in time a little bit and say, well, how do we come up with those vectors? Well, if we know the magnitude and the angle with the easterly direction, remember this is a 0-degree angle, we could say that V is 15 degrees. All right. So we're talking, 15 degrees, 20 knots multiplied by the cosine of 15 degrees, with the sine of 15 degrees. And then W is equal to 2 multiplied by the cosine of 45 degrees, the sine of 45 degrees. All right, we can clean this up, but ultimately we want to find the dot product. So we don't want to go too crazy because this is all just going to be simple calculations. We already know what the bottom is going to be, though. We already know the bottom is going to be a value of 20. So I'm not worried about that. We just got to get V dotted with W. All right. So V dot W, I'll do this in red, is going to be 20. Well, let me show the intermediate step. I don't want to skip too many steps. Otherwise, I become a textbook. I become the very thing I swore to destroy. Come on, son of a gun. All right, so yeah, just a quick little in purple. 20 cosine 15 degrees. 20, got hung up there. 20 sine of 15 degrees. Two cosine 45 degrees, tripping over the iPad here. 2 sine 45 degrees. Not letting me undo. All right. Yeah, like I said, just so I don't skip too many steps. So multiply the corresponding parts, add them together, and we'll have our dot product. So it's 20 cosine 15 times 2 cosine 45. So that's going to be 40. My undo button is struggling here. 40 cosine 15 degrees, cosine 45 degrees, plus same deal, just with sines. And that's all going to be over 20. So that's the magnitude of V. So we just got to crunch that. All right. In degree form. So 40. I mean, you could simplify too, because we have a common 40 that can be factored out and canceled, but you know, I didn't think of that, so here we are. Cosine 15. And if you wanted to, if you really want to get silly with this, you can get the difference rule for cosine involved and really clean it up. But, you know, maybe I'll do that in a sec. All right, so you get about 1.732. So that's the contribution of the water that's acting, you know, the current that's acting in the direction of the boat. So if we add that on to 20, and round to the nearest 2 decimal places, we're saying approximately 21.73 knots. All right. So it gives it a little bit more context, but it also, it doesn't seem like it's easier to do, but it's actually pretty straightforward. You know? Yeah. So just really quickly, if we had recognized, or I got to be fair about this, if I had recognized, I was the one who was asleep at the wheel here. I hate when people do the whole we thing, like lump everybody in with their mistake. No, I made that mistake and I'm proud of it. I'm the king idiot here. Yeah, so we had a common 20 that could have been factored out. So really, in the end, there's a lot of other things that we could have done, but the approach that I kind of had in mind as sort of like a little bit of, with a little tinge or twinge of regret, would have been if I factored out the 40 here. We'd have this expression, which is the expanded form for a sum angle for cosine. All right, so cosine plus sine. So we would be saying cosine of 15 degrees minus 45 degrees. The expanded form, that'd be cosine of 15, cosine of 45, plus sine of 15, sine 45. The signs are always opposite there. We'd have that coefficient of 40 in front. All right, so that gives you a cosine of negative 30, which is the same as cosine of 330. Which is radical 3 over 2. So you get 20 radical 3. And then you cancel that with this 20, and you get radical 3, which is 1.732, blah, blah, blah. So we could have done all of that. So alternate. And it's a slight variation on the approach, but a little bit more of a reward for knowing and recognizing a trig relationship. So if you're iffy on your trig relationships, then just hit up those last few pages in the Unit P packet, because they go a long way. All right. But yeah, you crank it out in the calculator, it does the same thing, and you're fine. But it's kind of nice. It's a cool moment when you recognize these relationships. Yeah. So the cross product. So the cross product is when you have two vectors, you can generate a third vector that's orthogonal to those two vectors. And that's what we're looking at here. It's computational. It's computationally, it's not difficult. The derivation of the formula is actually pretty epic, but for a different day, I suppose. So I'll actually get you started on the derivation. I'll kind of talk to you about the basics of it, but then we'll actually kind of jump to the shortcut rules pretty quickly. I'm not actually going to finish the derivation because, in all honesty, the derivation for the cross product is a solid page of notes. It's like a class in and of itself. So, I've gone down that road before. I have a video on it. I can post it, but that video is like an hour long. I'd rather see if I can try to streamline it down, so it's only maybe half an hour, 45 minutes. I don't know if I can make it any shorter. We'll see. But anyway, cross product, again, is going to give us a third vector that's orthogonal to the first two. All right. So what we're saying is that we have two vectors, u and v. And I'm going to create a three-dimensional system here. I'm going to create the vector u. Going off and it won't let me. Okay, there we go. Vector u. And vector v. Actually, I'll make this one u and this one v. All right. They could have any relationship with one another. They don't necessarily have to be orthogonal. They just have to be two non-zero vectors. All right. So I'm looking at, I got my x, I got my y, and I got my z. All right. What we're saying here is that there's a third vector that we're going to call vector w. That's orthogonal to these two. All right. So it's just a question of what it would look like. It's going to come somewhat out of the page. So I'm just going to kind of eyeball it here and say that this is my vector w. I'll move v down here. And I'm telling you that that is perpendicular to the v vector, but it's also perpendicular to the u vector. It's definitely off. I'm not happy with that. It should be more like this. Bring it back. Something like that. But I mean, I don't know if it's ever going to look perfect. It's actually going to be kind of like masking V, so I don't want to make it too close, but it does have a look where it be coming right out of the page. I'll make it dashed so it's a little bit better, or at least it stands out more. but you're going to have that vector be orthogonal to the other two. All right. So it could also be going in the opposite direction where it could appear to be going downward. All right. So what we could do is kind of move it down here so it looks a little bit more orthogonal. That's a possibility. But if you want to go with the more basic possible cases, something that's really obvious, you don't even have to consider any of this stuff, because I could say, wait a minute, doesn't that make the X, Y, and Z axes hold that orthogonal relationship? And I say you're absolutely right. All right, because if we have the U vector on X and the V vector on Y, then the W vector would necessarily have to be either Z, you can make it straight, can't, I'm gonna hand it, draw it, or negative Z. All right, we'd have the perpendicular relationship here, and we'd also have the perpendicular relationship here. All right, same thing on the bottom end, right? And so this would be our W, and this would be negative W. All right, so that's a way to do it. That's a way to visualize it, but it's not just limited to those axes. All right, so that's what makes it challenging. And also making a determination of, well, which one would it be? Would it be the W or the negative W that is the one that we would call the cross product between U and V? All right, we'll get into that. There's something called the right-hand rule that'll help us make that determination. All right, so the way the derivation actually starts off is by carrying out the process of dotting U with W, and then also dotting V with W. If you dot U with W, you're looking at U1, W1 plus U2, W2 plus U3, W3 is equal to 0. And then all the same stuff just with V's. So V1, W1 plus V2, W2 plus V3, W3 is equal to 0. So then what we'd have to do is solve this system of equations for W1, 2, and 3. All right, now you could do it algebraically. Like I said, it ain't pretty. Or you could do it using a linear algebra approach. All right, that's when you start getting into inverse matrices and things like that, and row reductions and all that good stuff. But the idea here is that ultimately we would be looking to solve for the values of W1, W2, and W3 in terms of U1, U2, U3, V1, V2, and V3. All right, so just a little taste of that. What you could do is use some kind of elimination, stack your two equations and say, all right, well, let's eliminate a variable here. And you decide which variable do you want to eliminate, and then go from there. You might say, okay, well, let's get rid of W3. And if you were to do that, then you'd look at these two and you'd say, okay, well, then these two have to cancel with one another. How would I cancel them out? Well, my second equation, I'd have to multiply through with the negative U sub 3. And my first equation, I'd have to multiply through with a negative V sub 3. And again, I'm not going to carry this through too much further because you can already see how much of a nightmare it would be. Or fun, depending on your perspective on things. But we'd have negative V3 U1 W1 minus V3 U2 W2 minus V3 U3, W3 equals 0. And we have negative U3, V1, W1 minus U3, V2, W2 minus U3, V3, W3 equals 0. And when you add them together, you get the cancellation here, and then you'd start regrouping and reorganizing and going from there, with the ultimate objective that you can, okay, now you can try to solve this one for W1. You know, combine like terms, factor out of W1, solve for it in terms of W2, then start the whole process over again, this time eliminating a different component, doing the same thing, getting a new system from that, and then doing it again for the third one. And before you know it, you'd have your solution. But like I said, it takes a while, and so on. Or you could use linear algebra, but the type of linear algebra that you have to use is kind of beyond the levels of this course. I can't just say, you know, like in the unit P packet, it's like, oh, just throw it in the calculator and get an answer. You know, it's not going to work for something like this. I'd have to actually teach you some of the concepts, and that's a little much, right? So for now, what we're going to say is, and then a miracle happened, and we ended up with a rule. And that rule is this one right here, which allows us to figure out the vector, the third vector that's orthogonal to the two given vectors, right? We will have to be able to figure out determinants, but we can either do that by hand. If it's a 2x2 square matrix, it's very easy to find the determinant by hand. I'll show you. Or you can put it in a Desmos calculator. It'll do it for you anyway. Either way, it's going to be pretty easy. All right. So I'm going to take you through a couple of examples, and then we'll go from there. All right. So we have P and Q. So right off the bat, we're already messing with things. P and Q instead of U and V, but it's the same idea. All right. So we're going to create a determinant with the first row being IJK. P goes in the first row, well, the first numerical row. We already got the first real row accounted for. That's going to be -1, 2, 5. Q is going to go in the remaining row, the last available row, 4, 0, -3. All right. So if you could follow the model works. You'd say, okay, I'm going to take my U2, my U3, my V2, my V3, and make those the coefficients, the coefficient matrix in determinant form of I. That's great. All right, a little niftier shortcut. I'm just going to create the framework here real quick. A niftier shortcut is to disregard the row and column that contains the component that you're looking for. Oh, what did I just do? I don't even know. I hit the wrong thing. I know it. So we're looking for I. All right, that's the first thing we're looking for. So in looking for I, what I'm going to do is I'm going to ignore the row and column that contains the I. I'm going to pretend they're not there. And I'm just going to write the matrix down that consists of the values that remain, the 2, 5, 0, and -3. For the J, I'm going to disregard the column and row that contains the J. I'm going to write down the values that I didn't cross out, -1, 5, 4, -3. And then for the K, I'm going to disregard the column in the row that contains the K and write down the values that remain after I cross out those entries, -1, 2, 4, and 0. Which will be the word of the day, entry. Okay. So then to find the result of these values, do it one of two ways. All right. One way is actually more trouble than it's worth. The calculator approach is more trouble than it's worth in this regard. All right. So of course, I'll show you that first. So Desmos.com. All right. If you look for it, I'll just kind of, you see math tools, you'll see an option for matrix calculator. All right. The URL is just desmos.com/matrix if you want to get there more directly. But all you would do is you would type it. You could type in determinant first, but the first thing you would do is type in your new matrix. So tap on new matrix. It's a default setting of 2 by 2 square matrix. So that's what we have here. So you type in 2, right arrow 5, right arrow 0, right arrow -3. Enter to lock it in, and then just tell Desmos to find the determinant of matrix A, the matrix you just typed in. That's one way. If it's a 2 by 2 square matrix, very easy though to do by hand. All you have to do is you multiply down the main diagonal, and then you multiply up the other diagonal, and then subtract. So diagonal down, which is -6, minus diagonal up, which is 0. All right. Multiply down the main diagonal, multiply back up the other way, and you'll get the determinant of the 2 by 2 square matrix. All right. Very easy. No need for a calculator for something like this. In fact, I actively discourage you from using it because I think it takes too much time. It takes more time to type it in to your calculator than it would to actually figure it out by hand. Now, you got a few minutes, you know, you're taking a test and you have a few minutes on your hands and you're thinking, well, I want to take a chance that I screwed this up, so let me just type it in just to be safe. That's a different story. That's not what I'm talking about here. What I'm talking about is like just common sense. Like you can multiply and you can add, you know, like that's easy. All right. So diagonal down, +3. Built-in minus sign, so minus. A diagonal up, 4 times 5, 20. So we're popping in a -17 here, but that -17 combined with the negative that's already there will make it positive. That'll help us along for our final answer. Diagonal down, diagonal up. So on the downward swing, 0, minus, on the upward swing, 8. So plus built into the formula, -8, K. And so, you know, I think this is perfectly fine for a final answer. Because, I mean, what are you going to do, right? The plus again, you know, so if you want, you know, just make it a plus and bring it all together. But that's how you find the cross product. Okay, we'll have to get into the differentiation and stuff like that, differentiation and integration. I also have a plus and a minus that's going to become a minus. So I could bring that together. But this would be my cross product. You could use Desmos and the matrix calculator to figure all that out for you. That's fine. But I would say probably a better way to do it especially if you have.
How'd you get to -8 in the last? And okay.
So you have diagonal down, which is 0, minus, and then 4 times 2 is 8. So 0 minus 8 gives you -8.
Why is it? It's not plus J plus K.
It is J plus K, but it's plus a negative, so it becomes negative just through the algebra. Because the determinant itself ended up being negative, like this computation.
Isn't it 4 of 2?
Yeah, 4 times 2, but it's diagonal down minus diagonal up. So -1 times 0 minus 4 times 2.
Okay, I got it.
All right. So I'm popping in GeoGebra. (3D). If you had any time practicing with the tech assignment, you know a little bit more about this than maybe you did a week ago. But even if you just watch me doing the tech assignment, you still got a little bit of a better sense. So to put a vector in -1, 2, 5, they call it A. We could change it to P if you need to, but I don't think it's a big deal. All right, 4, 0, -3. Same deal. We would want vectors. Vector for A. Vector for B. Now, you can just visually determine it. You know, you could put in your cross product. In this case, it would be -6, 17, -8 as your other point, and that would be fine. But you can also have Desmos do it for you. Just by typing in the command cross, I said Desmos, I meant GeoGebra. Just as a general rule of thumb, between Desmos and GeoGebra, I have this tendency to say, okay, well, if I don't know one way or the other, I just start typing in the thing that I want it to do. And if it'll do it, it'll start letting me know with a drop down in GeoGebra, or it'll start changing it from italics to regular font in Desmos, right? But bottom line is, it gives you the cross product here of -6, 17, and -8. So that's great. It doesn't appear to have plotted it though. Right? If it did, it may have just plotted the point. Right? So it gave us the cross product as a point. That's okay. So what I'll do is, if I actually want to see it in action, I'll type in vector. And then I'll tell it vector C and let it create the vector going to that point. Now what I want to do is I want to see that this is actually orthogonal. No, it's kind of hard to tell. It looks like it could be. I mean, it is, because the math is right. But if you get the right perspective, it starts looking a little bit better. Sometimes turning the axes off gets the job done, because when you do that, then it starts really looking a little bit better, because sometimes those axes are a little bit of a distraction. But you get the right angle here, the right angle to show the right angle. And it does appear to be perpendicular with vector A and also perpendicular with vector B. All right. So it takes a little doing to see it, you know, because when you do it like this, it's like, I don't see anything. Kind of like in Top Gun when he's trying to find, I'm trying to get my target lock. Point C is the MiG. I can't get him, you know. But then once you kind of lock in on it, it's pretty easy. You know, you just got to get the right angle, the correct angle. So there you go. All right. So could be more trouble than it's worth, though. You spend a lot of time playing around with this, trying to make it play out the right way, when really you just wanted to verify a simple computation. Right? So sometimes you just roll the dice and hope for the best.
Professor,
Right? Yeah.
this problem comes out in a test, you expect us to show the matrix equations, or?
No, it all
sort of-
depends on the type of question, because some of them are going to be multiple choice, and I'm not going to need to see work for those. And some of them are going to be free response. And in those cases, I might ask for some work. I can tell you that I typically reserve the free response questions for the ones that involve calculus. So, you know, I don't want to commit to one way or the other, but I would not expect to have to show these computations. Right, so as much as I can tell you without telling you, that's my answer.
Okay, thank you.
No problem. Now, number two is an interesting one because it's a question of anti-commutativity, commutivity. All right, so I can create the cross product or determine the cross product between U and V. And you know what I'll do here, just to keep it fresh, I'll just clear it all. I'm not going to save it. Get rid of this crap. I don't need the plane. Grid's fine. Plane I don't like. All right. If you just want the vector, that's the big bugaboo when it comes to these. You can put the vector in as a vector and then the coordinate 0 to 1, and it'll plot it. It doesn't look very pretty. Oh, okay. Well, it didn't save my work because it still got bogged down with that other notation there. All right, so I just got to get over here and really dive in. The regret of doing this on a tablet. All right, so you can see here, you don't have to put it in as a point first in order to come up with it as a vector. All right, so just so you know, because you can just go right to it. It's just most of the time we need to reference the points also, so it tends to be worth it. But in this case, it's not going to be necessary. So I'm going to get those values in. I got to get double parentheses, one for the vector command and one for, you see. And the thing about GeoGebra that you're going to find out, if you haven't already, is that it's very unforgiving. When you make a mistake, it's like, nope, do it again. And so double parentheses, 3, -1, 0, then lock it in. So we have our two vectors. All right, floating in space there. They look pretty good. They look already kind of orthogonal to begin with, but maybe not. So then I want to cross these up. And again, this is where I run into trouble because my drop down is in the way of the thing I need to hit. So what I do is I just kind of hit on something that I know is not going to interfere. So I just hit on that Greek letter tab, and then I hit the thing that I want. And then I'm saying it's U and V. So U, comma, V, and it'll give me the cross product. Now, in this case, because I had it cross two vectors, it gave me a result that is a vector. Before I told it to cross two coordinates, and it gave me a result over the coordinate. Right? So it at least understands that part of it correct. So U cross V is 1, 3, negative 6. So what I want to know is V cross U. So what I tend to do here is try to do a duplicate, if it'll let me. And again, easier to do on a laptop, but I'll do V and U and hit enter. And you see, the only thing it did was it flipped the direction. It changed the signs. So it became -1, -3, and 6. All right. So the direction in which you cross two vectors actually matters in terms of the output. All right. So let me just change the color on this if I can. Settings. Okay, it didn't take. Settings, color. Okay, that's what I want. Oh, I guess I just created the color and I didn't put it in. All right, so that's the other vector. So same type of vector, just going in the opposite direction. So that's what the result of crossing in the reverse direction gives us. It's called the anti-commutative property. All right, so actually let me bring this back now. So that's this relationship here. So it really actually does matter the order in which you cross two vectors. All right, so we got to be mindful of that. And the challenge is making that determination without always having to resort to GeoGebra. All right, so let's take a look at number 3. It says use the cross product properties to calculate 2i cross 3j cross j. Now we have the multiplication by a constant rule. That actually allows us, I can kind of cut to the chase on this one. It allows us to pull out the constants because you see in this rule, the constant can be attached to the U or the V, but it still factors out of the whole thing. So for this piece, I'm really looking at 2i cross 3j as being the same as 2 times 3 I cross j. Let me fix that I. That became an I. For some reason, it should have been a j. I don't know why. All right. So this is really the same as saying 6 I cross j. All right. So we need that result. It's just a question of, okay, well, what is I cross j? We could do it in Desmos, but we could also kind of use a little bit of common sense because I is a vector along the x-axis, j is a vector along the y-axis. Maybe I'll do it in GeoGebra and I'll use that to show you how it all plays out. How about that? We'll kind of bridge the gap here. I still like it. All right, so I'll put in a vector. 1, 0, 0. That's my vector I. And then vector my j, 0, 1, 0. All right, so you could see here that they're on the x and y axis and that the cross product ought to be on the z axis in some capacity. So what we would do is we would cross u and v. And you see that gives you the the k vector. So this gives you a result of 6k, which is all well and good, but the question that's got to be floating around in somebody's mind is, well, how do we know it wasn't negative k? Right? And so what we do is we use what's known as the right-hand rule. And so it's kind of tough to demonstrate over a computer. And I thought, honestly, I never did. I used to have a diagram in here, or at least I intended to have a diagram. What I'll do is I'll post a diagram up, a GIF that'll demonstrate it. I had it, I don't know where it went. But what you do is you place your fingers so that your index finger is pointing along your first vector, in this case, U or I. Your middle finger is pointing along your second vector. So these are your two vectors. Your index finger is the first vector. So in this case, U or I. And the second vector, the V or the J, is your middle finger. I'm holding it like this because people think I'm flipping them off. Wherever your thumb is pointing is the direction of the resultant vector, the cross product, right? So if you look at this diagram, the way I have it oriented, I did it like that on purpose, is so that you can actually put your fingers to the screen and say, okay, my index finger is going along U, my middle finger is going along V, where's my thumb going? My thumb is going up, all right? So then if it were the other way around, takes a little doing, but let's see if I can get there. It just never really wants to let me do it. All right, this I think, let's see. Nah, because the issue that you run into is with GeoGebra, it'll never, at least unless you toggle the view settings, it won't allow it so that the z-axis points in the downward direction. You could change a setting to allow it to happen, but then you run the risk of never changing it back, and that becomes a problem, right? So what I do generally is I say, okay, if I can manipulate the graph so that the opposite of what I want is visible, then I can verify with the right-hand rule what direction I don't want to be going in, and then the result will be the direction I do want to be going in. Right? But like I said, I'll send out an animation later that illustrates all that. I just got to put it on my list of things to do. Right. So we have the result of the left-hand side, which is 6K crossed with J. All right. So 6K crossed with J is really the same as 6 times K crossed with J. So then I just got to figure out what K crossed with J is going to be. Well, I know where K is. That's the vertical axis. All right. J is my y-axis, and so if I can actually manipulate this using my right-hand rule, based on this orientation, my index finger should be going along the z-axis, my middle finger should be going along the blue axis, and my thumb will then point where the result ought to be. The result ought to be in the direction that is negative on that red axis. That's the x-axis, which corresponds with I. So this should be negative I. All right, so 6 times negative I would be negative 6I. But you can verify that in GeoGebra. Actually, that's right this time, right? Because what I'd be saying is K crossed with J. So if I know that W represents K, then I can cross W with V. Put a phi in there for some reason. And it gives me a negative 1, 0, 0, which is the negative I vector, right? So then you can see with the right-hand rule, I mean, it's kind of hard because my thumb doesn't bend that way. And last time I did that in this class, virtually, it was terrible. I pulled a muscle in my thumb. I paid the price for like 3 weeks. It sucked, right? So It is tricky with the right-hand rule, but I'll like I said, I'll send out an animation later. I honestly, I thought I had a link to it in here, but I don't, for whatever reason. So what I'm going to do is I'll ask you to look at number 4. Numbers 5 and 6 are just rule-based. So what I'm going to say is try to tackle those on your own also, because we'll talk about the derivation of the rule next class. But for now, it's just working on applying the rule, which is the magnitude of the cross product. All right. So that brings us to the end for tonight. You'll notice, and you'll see here that after triple scalar product, we get into lines, planes, and then vector valued functions. You'll notice on Blackboard that I changed the title of the unit. It had originally had differentiation in there, specifically partial differentiation. I think I got a little overzealous, and so I dialed it back. So it will the test, when we get to it, we only have 2 more days of class before the test, if I'm not mistaken. But those the topics that'll be on it will not include any partial derivatives. So we're not going to get through this entire packet, obviously. But I didn't want you to think that I was going to throw some topics at you at the end and be like, oh, learn these on your own for the test. It's not going to be like that. Also, what I'm working on right now is taking the test from last semester that I gave on Blackboard, which is not yet available to you. I'm taking that, I'm cleaning it up a little bit, and I'm making it a practice test for this upcoming unit test. And that should be available by the end of the weekend. If not, it'll be ready soon, and I'll send a message out. I'll send it out on the announcements when it is. Right. So that's stuff that you can look forward to. Hopefully you find that to be helpful. So I'm going to stop